Let's do another fun momentum conservation problem. Let's say that you're on a raft and the raft is in the water and you float that raft up to a dock and you're on one end of the raft far from the dock and you walk along the raft towards the dock. So you're going to walk in that direction. Let me make that walking vector a different color. So you're going to walk in that direction at speed v. What happens when you walk in that direction? Remember that momentum of a closed system must be conserved. So when you walk in that direction, you have momentum. And what I didn't say is that you had to have started from rest. So when you start from rest and then you change your momentum to mv in that direction, then something else must get momentum of mv in the other direction. What else is there? It's the raft, right? You and the raft are a closed system. You exert a force on the raft exerts a force back on you. If you exert a force in order for you to move forward, you push the raft backwards. The raft must move in that direction at some speed v. So I'm going to say v raft and v u. Okay. So what happens when you move forward, the raft moves backwards. And we are assuming that the water is frictionless, right? So I'm not even going to write that down. We're going to assume the water is frictionless. And the squeak is my chair again, sorry. But anyway, so then you try to get to the other end of the raft, and the raft is not next to the dock anymore. Of course, if you've got an oar in the water, then you can create friction. But if you don't, what happens when you move to the left, the raft moves to the right. So let's just ask, by the time you walk the length of the raft, let's assume everything's frictionless. If you walk the length of the raft, L, relative to the raft, how far has the raft moved to the right? To answer that question, we have to assume some masses, and let's just say that the raft is like something like a canoe, which might be twice your weight, right? So let's just say that the mass of the raft is twice the mass of you, and I'll just say the person is m sub y, you, or y could be somebody whose name starts with a y. Yuri. Using momentum conservation for two bodies, this is not the most trivial question to answer. So it's kind of a fun question to think about, because the problem is that you don't actually move a distance L, you move less than L, because as you move to the left, you move L relative to the raft, but the raft is moving to the right, and so relative to the dock, you move less than L, right? Because where it's going to finish up is, by the time you get to the left end, the raft will have moved to the right. So relative to the raft, you moved L, but you have not moved L relative to your initial position. You've moved something less. Let's say that the raft has moved, let's just give it a distance. Let's say that the raft has moved, some distance. We'll just give it a distance. Let's say that this distance the raft has moved is, just call it x sub r. So the distance that I have moved is L minus x sub r. Relative to the dock. So if our coordinate system is this coordinate system here, then we can say that the raft has moved xr over, the end of the raft has moved xr in that direction, and I have moved a distance L minus xr in that direction. Trying to solve for is xr. How far does the raft move? That's the distance xr. xr equals what? Okay, so we can do this from a momentum conservation point of view. We can say that initially if I'm moving, initially, there's a number of ways to look at this, but let's just look at it from a momentum conservation point of view. Initially, before I start, let's just say, we in the top picture, initially we're sitting still. Then I start walking to the left, the raft starts moving to the right. So before I start walking, the total momentum of the system is 0. After I start walking, you're going to have that the momentum of mu, vu plus the momentum of the raft, mr, vr, is equal to 0 after you start moving, right? Because the momentum before is equal to the momentum after. So these are the velocities once you start walking. So what I'm trying to figure out is how fast will the raft be moving while I'm walking on the raft. And that's what this is going to give me. And then we can just say, okay, so mu times vu, which is vy in the minus j direction, minus x direction. This is, we can just say that's in the minus x direction. If we already defined this as the plus x direction, plus m raft, which is 2mu times v raft equals 0. So therefore, v raft, the velocity of the raft, must be 1/2 vu, 1/2 vu in the plus x direction. Momentum conservation, we showed that if I keep on saying me, if you are moving at 4 meters per second to the left, the raft, because it's twice your mass, it must move at 2 meters per second to the right. If you were the same mass, if you were moving at 4 meters per second to the left, the raft would be moving at 4 meters per second to the right. But that's what momentum conservation tells us. The other way you could look at that is from impulse point of view. You could do an impulse point of view and you're going to get the same answer. That the raft moves at a velocity that is relative to that is equal to your velocity times the ratio of the masses. The ratio of the masses. Okay. We know how fast the raft is moving. We need to know how long it is moving. How much time, right? So because remember, we're looking for the distance that the raft moved and the distance that the raft moved, right? The distance that the raft moves is equal to the velocity of the raft times the time of the raft, or the speed of the raft times the time of the raft. This is all one-dimensional. So that's just one-dimensional kinematics. Distance equals rate times time. I now know the rate is 1/2 times your speed, and now how much time? So we have to figure out the time. Okay, we figured out the speed. I want to know how much time does it take to go from the top picture to the bottom picture, and this is assuming that everybody's moving at constant speed. This is assuming that. Okay. What we do know is that the amount of time is, you could say, for example, is the distance that I move. Distance equals rate times time. Yeah, the distance that I move, which is L minus XR, divided by my you, not me, your speed, VU. So that's the time that it takes you to move that distance, so that's the time. It's just the distance that you move divided by the speed that you move. That's the time. Kinematics. So therefore, x that the raft moves, which is equal to the speed that the raft moves times the time that the raft moves, is this. And we also know that v raft is 1/2 of VU. And so we know that x raft is equal to L over 2 minus x raft over 2. Therefore, right, just multiplying that out, solve for x raft. Therefore, 3/2 x raft equals L over 2. Therefore, x raft equals L over 3. The raft moves 1/3 of its length by the time, so x raft is 1/3 of L. Okay, there you go. A fun problem to try to figure out, but there is another way of doing it. And the other way of doing it is a really important way, which is how we started this chapter and how we're going to finish this chapter, is talking about the center of mass. Instead of talking about you and the raft separately, we can just talk about the center of mass of the system. Do this from the center of mass point of view. The center of mass of the system is as if everything, all the mass in the system is concentrated at the center of mass. What's the momentum of the center, what's the momentum of the center of mass? The momentum of the center of mass of the system is 0 to start with. That means that by momentum conservation, that the momentum of the center of mass is always going to be 0. It may not, in this case, it's 0 to start with, but in another situation, the momentum of the center of mass must be conserved. So the center of mass is treating the whole system as if it's one thing at the center. And so the center of mass of a system is conserved. And we could have, every momentum problem we've done so far, we could have done from the conservation of center of mass, conservation of momentum of the center of mass, and just said that the center of mass momentum doesn't change. So the center of mass momentum doesn't change. In this case, the momentum of the center of mass is zero because nothing is moving to start with. So the momentum of the center of mass is always zero. Even when you are moving to the left and the boat is moving to the right, the momentum of the center of mass must still be zero. And that's what makes the raft move to the right as you move to the left, because wherever the center of mass of the system is, and let's just see if we can figure out approximately where the center of mass is. Let's look at the top picture. Center of mass of the raft is at its center. Center of mass of you is at your center. So if the two were equal in mass, the center of mass would be halfway between, but the two are not equal in mass. The raft is a little more massive, so the center of mass is actually to the left of that, and the center of mass is going to be a bit closer to the center of mass of the raft. So here's the center of mass of the system. So the center of mass of the system must always be in the same place. It doesn't move. So as you move to the left, the raft moves to the right so that the center of mass stays at that position. It never moves. And what is the position of the center of mass? Again, we can say, okay, here's your center of mass, here's the raft center of mass, and the center of mass. I probably drew the raft. Yeah, I drew the raft moving a little too far to the right. But anyway, center of mass doesn't move. So, and that's because momentum is conserved. Momentum is conserved for the system, or momentum is conserved for the center of mass. So that means if the center of mass doesn't move, we can write down the center of mass before you go anywhere. Mass of the system before we go anywhere. So we're just looking at the top picture. That's the center of mass of the system. It's going to be the mass of the raft times the position of the center of mass of the raft. Let's call our x equals 0 at the dock. So the position of the raft, x sub r, well, here, the mass of the raft is twice times your mass, so I'm just going to do that, 2 mu. The position of the raft is 1/2 L from the dock, and your mass, mu, your position from the dock is a full L, right? And so then we add together 2 mu plus mu, so that's 3 mu. So the position of the center of mass of the system is given by this. That's not momentum conservation. That's just the position of center of mass. So that equals 2/3 L. That's where the center of mass of the system is. The center of mass. Let's find a different color. Purple. The center of mass of the system, x center of mass, is 2/3 of the way along the raft. So that does not change. X center of mass after it moves, because the momentum is 0 of the center of mass, in this case, because it starts at 0, it finishes at 0, center of mass can't go anywhere. Center of mass after you move must still be at 2/3 L. So let me go to another page. So the center of mass is 2/3 L, so we can say after it moves, center of mass, x center of mass, we can say prime, but it's still 2/3 L. And that is m raft, x raft, after it moves, plus mu, xu, after you move, divided by m raft plus mu. And so then we say m raft is, 2 mu. The position of the raft, right? That's the center of the raft. If the raft has moved over, and we're pretending this is an unknown, xr, right? The position of the raft in the second picture is going to be xr plus 1/2 L, xr plus 1/2 L. That's the position of the raft. The position of u, mu, the position of u is xr, that unknown xr, how far the raft has moved to the right, because that's your position, you're right there, a over 3 mu. So now we have simply one unknown because the mu's cancel, and x raft is the unknown because we've got it equals to 2/3 L. So here, let me write this out. 2/3 L is equal to, I canceled the my's. We've got 2 times x raft plus 1/2 L plus x raft over 3. So therefore, solve for x raft, and you find the easy algebras. Do the algebra, and you find x raft is L over 3. Check. That's what we found before, and this was from a simple center of mass point of view, conserving the momentum of the center of mass. Okay, that's probably it for the examples in this chapter. Have a wonderful day. Bye-bye.